Welcome to the 9th lecture in our course. This time we will focus on the particle filter, which is yet another method for nonlinear filtering. However, as you will see during this lecture, it's rather different than all the other methods that we talked about previously. So, let's get started. Up until now we have focused on Gaussian filtering. That is, filters that tries to approximate the posterior as a Gaussian density. Although these are very useful in many applications, they also have their limitations. Examples when Gaussian filters do not perform as well is, for example, when the process or measurement models are highly nonlinear. In this case, the approximations made in both the EKF and the sigma point methods will be too poor. Another related example is when the true posterior density is significantly non-Gaussian. A multimodal density is one example of this. In this case, we can simply not accurately describe the posterior as one Gaussian. So, we see a clear need for additional techniques to handle also these cases, and one such technique is the particle filter. The basic idea with the particle filter is to approximate the posterior using a more general, non-parametric representation. That is, we describe the posterior, p of xk given y1 to k, using a weighted set of particles, where each particle, xki, represents one possible state realization, and the weight, wki, represents how probable that particular state realization is. So if we draw this, we have the probability of xk given y1 to represent is then represented by a set of particles xk1, xk2, xk3, and so on, and each of these particles are represented by a Dirac delta function, and the height of this is then given by the weight, in this case wk2 for the second particle. So during this lecture we will see that this is a very flexible representation, that it has some convenient consequences. For example, we can use the fact that each individual particle, which density is modeled as a Dirac delta, has no uncertainty associated to it. So compared to other methods, in the particle filter we can often assume that we know the true state. Filtering using a particle filter essentially is performed by first propagating our particles from the previous time instance to the new time, and then updating the weights. In the basic version of a particle filter, called a bootstrap filter, the particles are propagated using the process model. So we draw new particles using a process model where we condition on the previous particle. The weight for these new particles are then updated by multiplying the previous weight of the particle with the likelihood of that particle. To illustrate how the particle filter works, we'll look at a short demo. In this demo, a robot is using a particle filter to localize in an office, and it's using observations from a laser scanner and odometry information from wheel speed encoders to do this. What you see here is a map of the office in gray. This is known to the robot. The green dot is the current estimate of where we think the robot is. The blue lines illustrate the distance measurements coming from the laser scanner. The red dots illustrate where each particle believes the robot is located. As you can see, to start with, we believe that each location is equal probable as the particles are uniformly spread throughout the office. Let's see what happens when we start receiving observations from a laser scanner and wheel speed encoders. As you can see, as we start getting observations, these will match well with some of the particles, and will match poorly with others. Particles for which the observations match well will then get a high weight, while particles for which it matches poorly will get a weight close to zero. As we continue, we see that the particles get concentrated to a fairly small part of the office. And even though we had no clue where the robot was when we started, After just a few observations, we're able to locate in which of the offices it's in. After this lecture, you should be able to explain the concepts of Monte Carlo sampling and importance sampling. These are the basic concepts that the particle filter is based upon. You should also be able to describe what particle degeneracy is and why resampling is useful. And last but not least, you should be able to implement your own particle filter.